Okay, the next reaction we're going to talk about is the hydrohalogenation reaction, and we're also going to talk about the hydration reaction because they're very similar. Okay, so we're going to start out with a simple alkene structure. So we're going to start out with isobutylene. And in this type of reaction, for hydrohalogenation, we are going to react it either with HCl or HBr. These are both good reaction partners. All right, so we're going to do our mechanism here with HCl first. Okay? And so the product of this will be across the double bond, one carbon is going to pick up the hydrogen, the other carbon is going to pick up the chlorine. In the case of the hydrohalogenation reaction, the halogen always ends up at the more substituted position, and our hydrogen will be at the less substituted position. And we'll talk about why this is the only product obtained. Okay, so let's go ahead and draw out our mechanism. I'll redraw our alkene. All right, so our alkene, and we're going to react it with an HCl molecule. Okay, and so in the first step of this mechanism, we're going to do a proton transfer. So we're going to protonate our alkene. So we're going to take our double bond, and we're going to have it pick up the H+, and of course we'll have chloride as a byproduct. So this can happen one of two ways. We can either put the hydrogen at the more substituted position or the less substituted position. So we'll go ahead and draw out both of these and sort of justify why we only get one product. So if we do hydrogen at the less substituted position, we will form a structure that looks like this, where we have a tertiary carbocation. Okay? If we have our hydrogen go to the more substituted position, right, we're going to form a primary carbocation. So as we compare these two structures, right, we know that tertiary carbocations are much lower in energy. They are more stable than primary carbocations. So if we had to pick a reaction pathway to go down, we're always going to follow the pathway that's lower in energy. So in this case, we are not going to follow the pathway where we form the primary carbocation, so we're not going to go this way. Instead, this is our next intermediate in our mechanism. Okay? From here, we have chloride as our counter ion. Now it's going to act as nucleophile. So here, we're going to take one of the lone pairs on chlorine and form a bond with the carbon that is positively charged, the carbocation. And so here, we're going to form a product where we have a hydrogen at the less substituted position and a chlorine at the more substituted position. It's important to remember that the carbocation is an achiral intermediate. So if we do form a new chirality center when we have nucleophilic attack of chlorine, we're going to form a racemic mixture. In the case of this molecule, we do not form a chirality center, so we're not going to form a racemic mixture. If we follow the other pathway, the pathway that's not preferred, again, a very similar thing is going to happen. So we have chloride is going to act as nucleophile. And so here, it's going to attack the primary carbocation. And if this happened, we'll form a different product where we have chlorine at the less substituted position and hydrogen at the more substituted position. So now we have two possible products. We know we only form this product here. So the product we form has a specific name, and it's called the Markovnikov product. Right? And the opposite of the Markovnikov product, where we form the other one, is called the anti-Markovnikov product. We can do a similar reaction. Instead of using HCl or HBr, we can do this in the presence of water. So we're going to do a reaction where we react an alkene. This time, we're going to use dilute H2SO4 for our reaction conditions. And so essentially, when we draw out our mechanism using dilute H2SO4, we're going to use H3O+ as our source of acid and our source of water, which will be our nucleophile. Okay? So again, we're going to form the more substituted product, which is the Markovnikov product. Okay? So in the very first step, we're going to have our alkene get protonated. So we're going to take H+ from our H3O+ and regenerate water. We're going to generate the more substituted carbocation, where we put our new hydrogen atom at the end, at the less substituted position. Okay? And water will be our byproduct. Okay? In the next step of this mechanism, water is going to act now as a nucleophile. So we're going to take a lone pair on oxygen and form a bond to carbon, specifically the positively charged carbon. And we're going to form our next intermediate, where we have a new carbon-oxygen bond, where we essentially have a protonated alcohol. Okay? And in a final step, we're just going to do a proton transfer to sort of clean up our structure so that we have a neutral structure at the end. So we're going to take a water molecule, we're going to do a proton transfer, so we're going to take one of our extra hydrogens away in order to form a neutral structure, which will result in an alcohol at the more substituted position and a hydrogen at the less substituted position. So our hydration reaction is all an equilibrium process. So when we use dilute H2SO4, we're converting an alkene into an alcohol. And if you think back to our reactions for forming alkenes, we can take an alcohol and convert it into an alkene, and we used concentrated H2SO4 in order to do that. So really the concentration of water is going to determine whether or not we favor an alkene product versus an alcohol product. If we have a high concentration of water, we're going to push the reaction from an alkene to an alcohol. If we have a low concentration of water, we're going to convert an alcohol into an alkene.